Hi there, welcome to the new video. Today we'll be talking about this paper, which is titled as Systematically Exploring Redundancy Reduction in Summarizing Long Documents. This is from researchers from University of British Columbia. So in this work, authors basically talk about various extractive summarization techniques and the way they address the redundancy problem in long document summarization. So if you see right, long documents are likely to have redundant text more than short text because of possibly elongated discourses compared to short text. And most of the existing neural network based methods for extractive summarization have focused more on scoring sentences rather than focusing on how to sample. That's why most of the methods that you see still use greedy decoding strategy, which usually results in redundant and suboptimal selection. And the authors also propose a couple of new methods and show that these could also be helpful with existing models to better deal with this problem. So yeah, that's what now we'll see in detail. But before that, I want to give a little overview on extractive summarization first so that everyone is on the same page. So consider a document D. You are supposed to do extractive summarization. Let's call this method E. So you could have had done unsupervised way or maybe in a supervised way. So whether it's supervised or unsupervised, the extractive model is supposed to do at least two steps. The first is called the scoring stage, where it will score every sentence in the input, where the score corresponds to the importance of a sentence being selected as a part of summary sentence. And then you have the selection. Now the selection takes care of, given these scores, how do you sample sentences from there. And usually you will find people settling down with greedy decoding, where the idea is to select top K sentences, where you define K based on certain heuristic, and you select them based on the set of scores that you get from the earlier stage for every sentence. However, scoring can be innovatively designed such that it also takes care of outputting diverse yet relevant sentences with high scores, rather than most methods that give similar sentences high scores, because of which the redundancy still prevails. Now talking about the scoring strategies, as we have already discussed, you could go with either supervised or unsupervised ways. You have many graph-based algorithms such as text rank, lex rank, topic rank, and so on and so forth, where the main idea is to define sentences as nodes in the graph, and you'll have some logic to connect those nodes. And then you apply some ranking mechanisms such as page rank or some certain centrality measures to get scores for every sentence or every node in that graph. And once you have those scores, you greedily select top K sentences as your possible candidates for the extractive summary. Whereas talking about unsupervised ways, you usually model this problem as a binary classification problem for a given sentence. So let's say you have a sentence, you pass it through your model M, it will say 1 or 0, where 1 being it should be included as a part of summary and 0 being it's not important at all. So you usually have a probability distribution from 0 to 1, and you can have certain threshold to decide on whether you want to choose a sentence or not. So for this task, people usually go about using ROUGE between the sentence and the abstract or some kind of a summary to select possible important sentences against which they train their extractive model. However, you can be innovative at this point and decide your ground truth such that you tackle redundancy up to a certain extent. So you could even go with something like MMR based strategy, where the idea is to select sentences that are important or relevant to the entire text, yet diverse enough to the sentences that you have already selected previously. So yeah, that's the entire idea of the extractive summarization. Now let's dig into the detail to what paper talks about. Then they talk about the matrix for measuring the redundancy for a given document. They use two metrics. One is the unique unigram ratio and the normalized inverse of diversity, where the unique n-gram ratio is nothing but how many unique words or combination of words do you use across all the possible combinations that you have. So the more unique words or the combination of words such as 2 words or 3 words, based on the varying value of n, the higher that number is, the higher the score would be. So this is something similar to lexical diversity, the way you calculate it. Okay, so now talking about the normalized inverse of diversity, this is defined using this formula, where higher the value of NID would indicate more redundancy. So for this to be high, you want this to be low. And since bottom part is a constant, you would want entropy of D to be low. And since entropy is more or less the measure of randomness, so which can be thought of as dependent on the unique words or the common words that you have in the entire text. And they're using entropy of unigrams. Okay, so let's say there are n unigrams. So the entropy of the text is defined as minus summation from x equal to 1 to n, because you have n words, p of x log p of x. So this is the value that you calculate. So the more number of unique words you have, you'll have higher entropy. And since you have numerator high, the entire value of NID would go down, which would indicate low redundancy. So yeah, that's the entire idea to how do you again calculate the NID matrix. So authors use this to show various long documents and their average n-gram ratios to show redundancy across documents. So in this figure, as you can see, if you go from top to bottom based on the datasets or maybe from right to left, you will usually see a decreasing pattern because the green and the blue are short documents and the orange and the pink ones are the long documents. So as you can see, long documents have lower unique n-gram ratio compared to short documents. So this was again one of the validations to why long documents suffer from redundancy, because the source document themselves have little high redundancy in them. Also regarding the NID, they again did the similar experiment. So for this table, if you see from top to bottom, the number of words severely increased from 429 to 6000 if you talk about the research papers. The NID metric, which was dependent on entropy, as it increases, the redundancy increases. So yeah, it's pretty clear, like for long documents, it's hard to balance between importance and redundancy. Then they talk about the redundancy reduction methods, where they play around with 3 possible techniques to how we can reduce redundancy in extractive summarization. The first one is to design a decoder that implicitly takes care of redundancy into account. The second is when you're trying to score sentences, you introduce an extra loss that captures the redundancy, and as per that you train your model. The third is in the sentence selection phase. Once you're done scoring, how do you select sentences based on that can also help us tackle redundancy. Okay. So now they talk about different methods under all of these 3 categories that we have seen. So let's go through that. So authors talk about 2 baseline methods. First is the naive MMR, and then we have ExtSum-LG. So against these 2 methods, they'll be comparing the other methods. So talking about naive MMR, it's a re-ranking strategy that people usually use once you get the scores from some primary scoring mechanism. So let's say you wanted to use supervised algorithm for treating this summarization problem, and you have a binary classification in place, which means given a sentence, it would output a score between 0 and 1, where if it goes towards 1, chances are very likely the sentence is supposed to be selected as a part of extractive summary. So once you get that primary scoring done, you use this strategy to re-rank those sentences again, such that you trade off between what is important that has to be part of summary. At the same time, you also want to make sure that you don't select similar sentences to have diversity in the selection. So it's usually defined by this mechanism. So this first term that you see is called relevance. How relevant is a sentence to the entire document? So consider Q as D, which is the entire paper, let's say, and S is one of the sentences in that paper. And the second term that you see is called the diversity term. You want to select a sentence SI that's least similar with already selected sentence SJ. So if you do this, this negative term that you see will go towards 0, and hence the value of MR will go up. So that way you're kind of re-ranking over there. This lambda is the parameter that's controlled by user. It is again a trade-off to how much importance do you want to give to relevance or how much importance do you want to give to diversity. So yeah, that's the entire idea of MMR. But let me also pictorially show you how this works. Let's say you have a document D that has k number of sentences. For every sentence in this document, you calculate the similarity between the sentence and the document D. So in this case, they calculated a cosine similarity based on the embedding representation of sentence and document. So you'll get some cosine similarity between 0 and 1. So in the first iteration, you'll be selecting on a sentence that has the maximum similarity. So you'll do it for all the i's that you have. So let's say third sentence has the maximum similarity with the document. You will keep this sentence aside in a set. Let's call it as M. So you'll put 3 over here. Then you'll again reiterate through all the sentences in the document D, but this time you'll subtract and you'll not iterate through the sentence 3 because it's already being selected. So which means you'll iterate through all the k-1 sentences that you have, and you would do the similarity with the document D, but at the same time you'll also do a similarity with the third sentence that you have already selected. So that's the negative term that we have, which is sim2. So you want to maximize the similarity with the document, whereas at the same time you would want to minimize the similarity with the something that you have already selected. So that way you're kind of doing a trade-off between what you want to select that's relevant but also diverse. So let's say this comes out to be 2, and so on and so forth. So yeah, I think now it should be really clear to how MMR is working. So let's move forward. So the next baseline that they select is called ExtSum-LG. So it's current state-of-the-art model on summarization on long documents. Okay. So you have a MLP as a decoder and cross entropy as the loss function. And once you're done scoring based on the sigmoidal output, the selection phase is still a greedy decoding, which results in redundancy. Okay. So yeah, it's a binary classification problem only because you can see this cross entropy term over here. So let's say you have these end sentences. Based on the sentence was 1 or 0 in the ground truth, one of these terms would be active and other would tend to 0. And then you'll get the value of cross entropy, which will propagate backwards to train the weights for your network. So yeah, now on these two, they play around by adding multiple variations. So it can be seen in this table as well. So we have discussed this naive MMR, and then we have discussed this ExtSum-LG. And on this, now they add all these variations, what you see. So A means you're playing around with decoder setting, B is you're adding extra loss function, and where C means you're playing around with the sentence selection mechanism. So let's see to all of these in detail now. So in this section, authors particularly talk about two kinds of decoders. First is called the SummaRuNNer Decoder, where the idea is like at any point I where you're trying to predict the probability yi for the sentence I to be a part of extractive summary, you don't just consider the sentence representation but also the saliency to how important this sentence is to the document D, but it's also a function of novelty where sum I is nothing but the hidden state representation of all the summary sentences that have been generated so far. So it's a weighted summation of that. Then you multiply by the weight WR and the hidden representation of the current sentence HI. And then you have the position encoding. The first one is called the absolute, then you have relative. Absolute as in if it occurs at the second position or the third position in the entire paper. And under relative, they basically divided the entire paper into certain segments. So in this paper, let's say for example, we have introduction, we have background work, then we have experiments, then we have results, and we have conclusions. So these could be our certain segments. So relative position basically gives a hot encoding to which segment does the sentence belong to. So again, you have a weighted function of both of these position encodings, and then you have the bias term. So then all of these things are used and passed through a sigmoid to get a logistic value of 0 or 1 for a sentence to be selected as a part of extractive summary or not. So if I recall correctly, they used a bidirectional GRU based method. So you have a first word level encoding. So these are all the words for sentence 1, let's say. At this position, you would get a sentence embedding. And similarly for sentence 2, sentence 3, and then you have a RN that runs over all the sentences. And since it's a many to many mapping, so for every sentence, you also output whether it should be a 1 or 0. So yeah, that is the entire idea for SummaRuNNer Decoder. And once you have P of yi for every sentence I, you basically use greedy decoding and then select top k sentences across all the sentences that you have to constitute the final summary. So this novelty term that you see, right, is taking care of the redundancy part, what we were talking about. But clearly here also it's taking it in an implicit way because it's one of the factors across many other factors that can be tweaked in to have higher probability for a sentence I. So clearly this is not directly supervised over here. So this is where the second method comes into the play, which is called NeuSum Decoder, which highlights both the drawbacks that I just mentioned about the previous work. And what they did was, they introduce a scoring function that jointly learns the sentence scoring distribution and the way you select those things. So this is defined by the scale divergence term, which takes in two distributions PT and QT, where PT is nothing but the softmax distribution across all the sentences that you have based on their scores that get normalized between 0 and 1. And Qt is a function of temperature based G tilde Tyi, where GTYI is nothing but a difference between the root scores. So here S of T minus I is like whatever sentences you have selected at this point, union whatever sentence you are about to select, what is the root score that you get with the original summary, minus the root score if you had just T minus 1 number of sentences. So if the root score increased, which means the selection that you have made is good. Otherwise, you could also get a value that's negative in this case, if this right term is greater than the left term. So to normalize this factor and to keep things between 0 and 1, they squash these values and pass it through a softmax layer, which is termed as G of tilde, which is an input over here, and which is then parameterized by temperature, which acts as a smoothing factor over here to kind of decide on if you want a peak distribution or more of a flattened distribution in the 0 to 1 range. So if you have noticed, like in the earlier case, we were doing the scoring separately and selection separately. There was no way like both of the information could be utilized and the model would mutually benefit from each other's information. But in this case, because we are using the scale divergence term as a loss function that measures the difference between two probability distributions P and T, where P being how we score and Q being how we select, we are trying to do the selection as well as scoring in such a way so that the distributions look similar, and that way the loss would also be less. So yeah, that's the entire idea for this NeuSum. Now talking about the third one, where they talk about the category B, where they introduce the extra loss RdLoss as one of the factors apart from cross entropy. So what they do is, so this is a typical loss that you would just have, like L is equal to CE, where CE is nothing but the cross entropy. At any time step T, you would kind of define if this sentence should be selected or not. But now they have defined a beta parameter that is controlled by humans to define how much weight do you want to give to deal with redundancy or not. So if beta is equal to 1, you are just doing typical cross entropy, you're not dealing with redundancy. If beta is equal to 0.5, then you give equal weightage to how do you select sentence, but at the same time you also decide on how do you select sentences that are not redundant. So if you see the LRD term, it calculates the similarity between all the pairs of sentences that you have along with the likelihood values. So if two sentences are highly likely to happen, but they also have a very high similarity, then you'll have a relatively higher loss compared to in case if you have sentences that have high likelihood but lower similarity. So yeah, that's what the LRD term takes care of. Okay, moving forward. Now jumping to the last section where they talk about explicitly reducing the redundancy in the sentence selection phase. So the first one that we saw was while decoding. The second one was you introduce extra loss function for explicitly handling the redundancy part of it. Whereas in this phase, once you're done scoring and all of that scores are generated, while selecting, what can you do to reduce the redundancy? So the first method is called Trigram Blocking. So here the heuristic is that instead of selecting the sentences greedily according to their scores, you calculate the trigram overlap between the current candidate and the summary that you have generated so far. And in case you find any trigram overlap, you skip that sentence and go on to the next one till the length limit is reached. So yeah, this is pretty much similar to what MMR does, but is much simpler, where you're just trying to reduce the syntactic similarity between what you have already selected and what you're about to select. So yeah, that's pretty straightforward. Let's move further. The next is MMR-Select. So this method works similar to how MMR works. The only difference it introduces is at this level. So if you can recall MMR, you would have a lambda times similarity of sentence SI with the document D. So this would have been a similarity function. Then again, you have a similarity function from every sentence in the document and the sentence that you have selected in the selected set. Here, instead of this first term, they introduce the likelihood of a sentence that you get from the model. And again, once you have these MMR scores for all of the sentences, you go about and greedily select top case sentences from there. So yeah, that's pretty much the difference that they point out from naive MMR. Now let's talk about the last model, which is MMR-Select Plus. So here they say like the main limitations of MMR-Select is that the sentence scoring phase and the sentence selection phase cannot benefit from each other because those are totally separate steps. So yeah, this is pretty true because you calculate this at the first step, then based on the scores that you get, then you go ahead and do the selection. There's no way like both of them can share the information to what you selected. Based on that, the weights could also get updated. So under MMR-Select Plus, they introduce this pipeline where D is the document. Let's say it has n number of sentences. It goes through a neural model that gives the probability of every sentence to be a part of extractive summary. So you'll have n probabilities. So once you get these probabilities, you go about implementing a greedy selection strategy and select top k greedy sentences from there based on their scores. And similarly, you also apply MMR-Select mechanism and select sentences based on that strategy. Here S is the ground truth summary that you have. So all of that goes to the module LRD, which is one of the loss functions what they talk about. That's weighted by a parameter lambda that controls the factor to how much you want to introduce this in your loss function. Then they also have a typical loss of cross entropy, which is based on the probability distribution that you generate for every sentence, which you calculate against the ground truth sentences that you have, which is weighted by 1 minus lambda because lambda ranges from 0 to 1. So based on both of these losses, LCE and LRD, you calculate the composite loss L. You do the backpropagation, you adjust the weight for your neural network such that P of yi, P of y2, all of these change. Accordingly, the MMR-Select set would change. Accordingly, the greedy select would change. And you'll have a new loss probably if it's lower, then which means the models have correctly learned the weight. So now let's see what this LRD loss is. So it's basically the difference of the root scores that you get from MMR-Select and greedy strategy, where you consider 1, 2 and L all the ROUGE variations and do an average, which is then weighted by the likelihood of every sentence, which will get affected based on the weights that you update based on the backpropagation algorithm and will be responsible for scaling down or up this ROUGE factor. So if you notice, if you have a high ROUGE score with greedy select strategy compared to MMR-Select, then this entire term would be negative and you already have a negative in front, which means this becomes positive and the loss increases. On the other side, if MMR-Select has a high ROUGE score compared to greedy select strategy, the entire term would be negative, which will then lower the original loss that you had. So which means R of S bar, which is the greedy select strategy, is acting as a baseline over here. You want to improve relative to this. So yeah, that's it for this one. Now they have experiments and all. So I think we are done with the paper now. So if you like such content, make sure to hit that like button and subscribe to the channel. Also share it across with your friends to whosoever is interested in such content. I'll meet you in the next one. Bye bye.